Okay, so this is intended to be a short summary and an example problem on basically solving pipe loss. It's based on a Frank White textbook on fluid mechanics, chapter 6. Um, this doesn't summarize everything from chapter 6, but it kind of focuses on major loss and minor loss. So few things we're going to cover today, primarily major and minor loss. We have seen major losses before, but it had a different name. It's called as a friction head loss. Uh, in chapter 3, where we have friction head loss in your energy transport equation, um, we didn't know how to calculate it yet. It was usually given to us. In this chapter, we basically learn how to calculate it. And we also have an additional term that accounts for other losses, as in minor losses. The friction factor F with Moody chart is for your major loss. Then finally, we combine those two losses and then into our energy transport equation. So, quick recap, your standard Bernoulli equation, um, basically, they're kind of like a total pressure you start with equals the final pressure you end up with. With a bit of work, you can account for stuff like friction loss, pump input, and turbine extraction or turbine loss. So that's your energy equation. Now, um, so you can find the power based on each of the terms as long as you have the component of the head. So if you want the, say, pump power to actually support the system, then you just need H pump. And similarly, if you want to find a power loss by friction, then you just find HF and then plug it into the equation on the lower left. Now, friction head loss, that's the one where we basically haven't been able to calculate yet. And a big part of chapter 6 is basically on how to calculate that. And then we'll also have another terms called your H minor. Uh, but without the friction head loss, which we also called major losses, especially in the context of chapter 6. They're basically the same thing as your friction head loss. We're given this equation to calculate it. F is a friction factor, non-dimensionalized. F changes depending on a few parameters, primarily your Reynolds number and the wall thickness. Oh, sorry, the wall roughness. Um, the rest are pretty straightforward. V is your average velocity within the pipe. D is just the pipe diameter. Oops, typo. There should be an E in here. Pipe diameter. L is the overall pipe length. So sometimes your diameter could be, say, a meter, and then your pipe could be running for kilometers. So you want to be very consistent with the units. So you want to change it probably all to meters or feet. And then G is just 9.81 meter per second square or 32.2 feet per second square. Now, to find F, you can use either Muti chart or the Hallan equation. On Kirkus, there's a PDF that highlights how to find how to use the Moody chart. So we're not going to go over that again. It's fairly straightforward. The Hallan equation here at the bottom is actually proposed by a professor in Norway, Professor Hallan, got this proposed in 1983. You can actually look up the paper. It's pretty short, 2 pages. The equation is quite good. The error is like 2% max. I think it's more accurate than the Moody chart, eyeballing it. But the Hallan equation has some restrictions, primarily that it only works in the turbulent region. So use both methods. So go into the Moody chart, look up roughly what you expect. Then you plug the numbers into the Hallan equation and give you a accurate F for the actual calculations. This way, you make sure that if there is a mistake on either method, you can catch it. Um, but you're not expected to have to use like a super accurate value from a Hallen equation. If you run into this in exam, Moody chart results or Moody chart F is also accepted. So we cover major losses. So now the minor loss, right? So the major loss is basically stuff due to frictions. The minor loss is basically other geometrical restrictions like, oh yeah, let's say there's a 90-degree bend, or like there's some kind of valve, or there's a sudden expansion. When you're trying to push fluid through a bend, 90-degree bend, it's gonna have basically some kind of loss of pressure. Uh, and if your system is quite long, quite complex, those minor losses, even though it's called minor, is not quite negligible. The equation, oops. So the equation is KL, V squared divided by 2G. So KL is the combined loss coefficient. So it's basically a sigma of K. So we have a intermediate system down here. And the idea is that you want K of every geometrical change. So one, you have a sharp entrance. That's your basically K1. Right. K1. And an open flow valve, that's going to have another K. Now, I was tempted to put a K on the pump, but we have H pump in the energy transport equation. So we actually don't need to include anything in terms of losses within the pump. It's going to be included in the pump head. Now, here there's a bend, K3. Here we have another bend, so K4. Finally, we have a half open gate valve, K5, and then finally a sharp exit, K6. So your KL is equal to sigma of K, which is equal to K1 plus K2 dot 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 plus K6. And then you times it by V squared divided by 2G. One thing I do want to point out, so when you have a system with a pump, sometimes the flow is going to be elevated, right? And on the left-hand side, that would be your set one in terms of your altitude. When your flow exits the pump, your datum gets reset. This is now your new datum. So I'm not sure if the set two is the tank or relative to the exit of the pipe, but technically this is your new altitude on, or basically the altitude gain on the right-hand side of the equation. Do not consider this part. That's gonna be part of the H pump. Yeah, technically we have gained some altitude, but anything that happens in a pump stays in a pump, including all the loss and all the energy added in. It's just gonna get represented as your H pump. So your datum resets when it exits the pump. To find K, usually it's either given to you if they want to be nice in exam, or they might give you a table. The K value changes depending on quite a few parameters, uh, especially things like, say, pipe diameter. There's two that I would say have it on your crib sheet. They're basically sharp entrance and sharp exit. So sharp entrance 0.5, basically what we have here. Sharp exit 1.0. So I'll say these two are the ones that you are expected to have on your crib sheet. Anything else will be provided to you either as a part of the question or in the H sheet that's provided in the exam. Okay, so we cover the major loss and the minor loss, and let's see actually how we solve all these pipe loss problems. So 6 steps guide, pretty straightforward. It's kind of like how for a drag flow you have a 4 or 5 steps guide. You follow the recipe, you're pretty safe for most of the problems. So first of all, calculate velocity v. Quite often, we're only given a flow rate, q or like m dot. So we gotta change it back to velocity. And that allows you to go into step two, calculate Reynolds number, RE is equal to rho VD divided by mu. There are two types of viscosity. This one is called mu. This one is called nu. Um, Basically, nu is equal to mu divided by rho. Nu is the kinematic one. Ooh, oops. And mu is the dynamic one. Um, so step three is finding your friction factor F. There's two sub-steps to this. First, Moody chart. So you locate, this is why we needed a Reynolds number, right? So you have the Reynolds number, you have the epsilon, and then you use the Moody chart to give you a rough estimate for F. Then you use the Hallan equation to both validate and give you a more accurate value. Step four is calculating the major loss, because now we have F, we have V, we have the pipe diameters and length. You have your major loss, HF, which is again the same as your friction head loss. Then the new stuff, minor loss, HM, you have to find KL. So you have to look at the system, combine all the Ks, and then times V squared divided by 2G. And finally, you plug everything into your new updated energy equation. Again, we've added your HF or a new HF, sorry, HM, minor loss. Yeah, this is beyond recognition compared to the standard Bernoulli equations now. And again, be very, very careful with the signs. It's very tempted to say or writing in and oh yeah, friction loss gotta be negative, right? No, keep it positive, keep it classy, just throw it in and scale it into the equation. The equation is basically ready. The only thing that should be negative is on the right hand side of the H pump. Quite often when you have pipe flow problems, the H turbine is zero because there's no turbine. But there's nothing saying they couldn't have both turbines and pump in the same problem. And to neatly summarize it, with a 6 steps guide, this is more abstract, more condensed. Have this on your crib sheet. Time is tight. You want to make sure you don't waste time trying to figure out what to do next. Faster you can finish a problem, the more time it gives you to double check your numbers. So 6 steps, pretty straightforward. So the example we have for today, just one, but this is kind of intermediate. There's two parts of it. The first part is quite straightforward. The second part gets a little bit more hairy. So we have a water pump system here. We're given pressure in PSIG. That means PSIG is pounds per square inch gauge. Again, you are expected to solve or deal with imperial units for the final exam. My advice is at least be comfortable to do some straightforward or simpler imperial units problem. So you don't have to rely on unit conversions all the time. It'll still work, but the more operations you do, the more likely you have mistakes. So the overall length is 80 feet. So I'm gonna write that down. L is equal to 80 feet. The diameter is 4 inch. Now, say feet an inch, so the diameter has to be converted into feet as well. Um, 1 feet is equal to 12 inches. So, you got 4 inches divided by 12, that gives you in feet, basically 1/3. Uh, what else do we have? So the original problems, you have to go to some sort of a tables or plot to find these sort of values. In an exam, the density and the viscosity would probably be in the crib sheet. The epsilon, they're either provided to you in a question or you might have to go look it up in a table. What else do we need? So we're given the flow rate. And yeah, I think we can start getting solved or start solving the problem. So again, step one, find your velocity. So Q is equal to 0.4 feet cube per second. Q is equal to area times velocity. We're ranging V is equal to 0.4 divided by pi r squared. This is basically diameter divided by 2. You can also have pi divided by 4, but I kind of like switching it to radius. Plug in their values, that gives you 4.58 feet per second. That's step one. Um, oh, I forgot. So, the pound force, the pressure, gauge pressure is given to us as PSI gauge. So we actually have to change that into per square feet because we're dealing with feet, right? This is like imagine your pressure is like per millimeter, you have to change it to per meter. So 1 PS, or sorry, to go from 6.5 PSIG to PS square, I guess, feet gauge. Remember 1 feet is equal to 12 inches, right? And these are square. So you have to go basically 12 square. Basically left-hand side times 12 square. And that gives you 6.5 times 144. And this will basically be in square feet. So keep that there. So this is P1 gauge. Also note the question is a little funny. Point one is actually right after the pump. So we don't actually have to consider the pump in this question, but quite often, you calculate it and then they ask you what kind of power you need to overcome the system. Then in that case, you put P pump in as a dummy so you can get a numerical value. So step one, find V, we've done it. Step two is your Reynolds number. R is equal to rho VD divided by mu. For velocity, sometimes we use V, sometimes we use U. They're interchangeable. The only issue is we have a lot of V, so we have volume, we have your mu, your viscosity, that kind, your kinematic viscosity, that is also lowercase v. So sometimes textbooks might use U instead. The values are given to us for the density, 1.94. We just calculate the velocity. Diameter again, don't forget to divide by 12. And mu is also given to us. That's going to give us a Reynolds number of 1.42 times 10 to the 5. And that's our step 2. For step three, it breaks into two parts. Um, First of all, with the Moody chart, epsilon divided by d. Again, epsilon is provided in this case. 0.00015. Be very careful with the amount of zero. Double check every time. With epsilon divided by d and Reynolds number, you can go into the Moody chart, and the F Moody is roughly 0.02. This is just kind of eyeballing it. And then we go into your equation, the Hallan equation. You plug in, F is roughly equals to 0.019036. I'll say generally for 3 to 4 sig fig is sufficient when you use the Hallan equation. And we're gonna use this one. So we've done all that. And we're gonna go into step 4, finding HF. This is basically your major loss. HF is equal to F L divided by D times 3 squared divided by 2G, 0.019036. Remember, F is dimensionless, so doesn't care metric or imperial. Actually, we're just gonna use 0.019, kind of smooth it out. Length is 80 feet, diameter is 4 inches, but again, we have to convert it to feet. V squared, we already calculated it. Again, G is 32.2. If you're solving the problem in imperial, do not use 9.81. It will crash and burn. Let's see, what else do we have? Right, you can just plug the numbers in actually. 1.485 meter. That's your HF. Then finally, well, not quite finally, we go to step 5. We're gonna solve your minor losses. Now, to solve the minor loss, you need the KT. So HM is, or sorry, KL, V squared divided by 2G. Sometimes you can find the K from the start when you write out some of the values or the parameters. We haven't done it, so we're gonna go back and look at the problem and then write out K. So remember, we're starting from point 1, and then we're gonna mark point 2 as here. So if you do have to start at the pump, or sometimes the pipe just kind of comes in, you don't see what's on the other end of the pipe, you can just assume it is a straight pipe that is not shown, and then K is equal to 0. You only have to consider the entrance if it's coming from a tank. So K n equals 0, which doesn't matter because we're starting after the pump anyway. Valve, so we're gonna have K valve, and then we're gonna have K filter. We have 2 elbows, so 2K elbow. And this is a sharp exit, so K exit 1.0. So we're gonna add that in. KL equals K valve plus K filter plus 2K elbow plus K exit. The valve is given to us by the question 2.8 because it's only half open. If it's fully open, then usually it should be 0. Filter, the K filter, that's what we're trying to find. So we're gonna leave that. The elbow, again, this would be either given to you as a question or you have to look it up in a table or a plot. And finally, K exit 1.0. The exit one is just you will need to have it on your crib sheet or remember it. And that give us a KT of 5.08 plus K filter. That's step 5. Oh, not quite yet. Ooh, almost made a mistake. That's just the KT. That's not the HM yet. Yeah, don't plug it right in. That would not work. So HM is equal to 5.08 plus K filter times V squared, which is 4.58 squared, divided by 2G, 32.2. Which is equal to 0.326 K filter plus 1.655. Then finally, you can actually go into step 6 to construct the Reynolds transport of your energy. See if I can drag the. Oh, I didn't copy the equation. Okay. That's all right. Let's write it out. E1 divided by gamma, E1 squared divided by 2G plus Z1 plus P2 divided by gamma plus V2 squared divided by 2G plus Z2 plus HF plus HM. Now let's have a quick look at the equation to, or sorry, not the equation, diagram. So again, point 1 is here. This is after the pump. Point 2 is here, so we don't have to include a pump. Point 2 is open to atmosphere. Remember, this is a reservoir. So V is equal to 0, and also P gauge is also equal to 0. And since V2, open reservoir, and gauge pressure is 0, we only need to include Z2. Z1, that's the datum, so that becomes 0. It's always nice working with Bernoulli equation or the energy equation where you get across out a bunch of stuff. Though just make sure you don't go trigger happy and cross out too much stuff. Make sure that the validate or the assumption is correct. So P1 gauge, we calculated this earlier, all the way back here. 6.5 times 144. Gamma is rho G, which is roughly 62.4. We want 4.58 feet per second square, and then 2G 0, that's your left hand side. The right hand side, 0 plus 0 plus Z2, that's 9 feet. HF, we calculated to be 1.485. And HM, we just have it right here, plus 1.655 plus 0.326K filter. One equation, one unknown. K filter equals 9.77 meter. Um, quite significant actually. Now, quite often they might ask you to actually change that to actually I guess you couldn't really change it to actually no unit. Oops. Yeah, K is a dimension as parameter. Um, 9.77. Actually, let's double check. Yep, it is dimensionless. So that is part A. Again, we're basically just following the 6 steps guide. It's kind of like a cookbook. That's the more straightforward one. Again, loss coefficient, that's just K. Now, part B, they turn the problem around and say, okay, what if, okay, we completely open this valve, so the K value is now equals to 0, and then we have a new K filter. What's the resulting flow rate? So when that happens, because there's less blockage, so the velocity is gonna change, the Reynolds number is gonna change. Your velocity, Reynolds number changes, your F is also gonna change, and it's kind of like a whole can of worm. And you have to use something called an iterative method. So you cannot go the conventional route of step 1 to 6. You kind of go the other way around-ish. You start from the final step, and then you work your way back, and then you're gonna jump between your F and your Reynolds number until you finally have like an F that can allows you to calculate your velocity. Um, I will say for Poppy, and I'm gonna include it in this video, but Poppy, the method itself for this sort of iterative process is quite intense. It's technically fair game in an assessment, but uh, we're not asking you to be a robot. That's why we have computers to do sort of iterative process. So we're gonna work for it. I'll say just kind of know how it's done, but I wouldn't spend too much time obsessing over it. K valve is 0 to 0. We got a new K filter equals 7. We are basically trying to find Q and V. So remember, we're starting from the bottom now. So step 6, you have to write out the same energy transport equation. A lot of the assumption still holds 0, 0, 0, because the locations itself hasn't changed, right? Uh, Again, this is basically pretty similar, but we're gonna update it with new values. So the first term is 15, that has not changed. However, the second term, we don't know the velocity anymore. V is not equals to 4.58 feet per second anymore. And then divide by 2g. Plus 0 equals 0 plus 0 plus 9. Now, HF, this kind of gets hairy because we don't know V and we also don't know F. Remember, F is based on your Reynolds number, which is a function of velocity. We technically know KL, but again, we don't know the new V. Let's plug in the numbers that we do know. F. The length and the diameter has not changed, which is good. Plus 9.28. Basically, I took the V squared divided by 2G out. So this is just your new KL. Okay, yep. We're gonna throw all the numbers that we do know to the left. 15 minus 9 equals v squared 64.4, 240f plus 9.28 minus 1. Where did the minus 1 comes from? I've thrown this to the right-hand side, and that becomes the minus 1. Because again, remember v squared divided by 64.4 outside the bracket. On the left, you have just 6. On the right, you have v squared 64.4 times 240f plus 8.28. And this is where the problem begins. We have one equation, but kind of like two unknowns, right? We need v to find f, but then we needed f to calculate v in this equation. And here comes the robotic part. The idea is that we guess an initial f and then go from there. So the f from part A that we calculated was, or from the Moody chart in part A or the equation, was around 0.019. So we are gonna use that. You can also use 0.02. So we're guessing f is roughly 0.019. If you're not sure, 0.02 is a decent one as well. Um, the reason is that if you look at the Moody chart on the left for your f, 0.02 has a pretty flexible range. You don't want to go something too high or too low. The closer your initial guess to the actual solution, the more likelihood that you will get it without extensive amount of work. So first guess of 0.019, you plug it, I'm gonna call it equation 1. That gives you 6 equals v squared divided by 64.4, 240 times 0.019 plus 8.28. V is equal to 5.486 feet per second. Also, the guessing is basically arbitrary. Arbitrary just means random, but random with a human factor. So if you guess a number randomly, then we usually call that an arbitrary number. It sounds a little bit fancy, and also, it's not really random because then it has a human factor included. Um, Now, this isn't quite done yet. This is just the first round. We need a second round where we update your Reynolds number because we have a new V now, right? So RE is equal to rho VD divided by mu with the new velocity. Your Reynolds number is now different, it's greater. All right, because V has increased. Uh, Now that we have a new Reynolds number, we are gonna go into, oh, you can go into the Moody chart, but with iterative process, I would advise against using the Moody chart because the error from the Moody chart when eyeballing it is astronomical and not good for iterative process. So we're gonna use the Howland equation, and that's gonna give us 0.01866. So kind of close to 0.019 of our initial guess. Uh, and with the new f, well, we gotta update back into our equation 1, right? Into our equation 1 again. Kind of see how this is such a painful process that I'm just turning into a robot. In an assessment, you would probably not be asked specifically to use which method. You should be able to solve the assessment with your Moody chart alone. And Moody chart is not very accurate when it comes to iterative process in this approach. So you can read between the lines if you want. So that gives us another velocity of 5.503 feet per second. Um, so it is still kind of increasing slightly. And we have to go into third round. This is why we have computers, right? With the new V, we have a new Reynolds number again. That's going to be 1.703 times 10 to the 5. With a new Reynolds number, we get a new Hallen factor, which is 0.018657. If we compare these two, close enough. And the idea is that once your iteration, the delta f, is small enough, let's say maybe less than 1%, you're good to go. So we're gonna accept f is equal to 0.01866 as our answer. And we're gonna accept our velocity of 5.5 feet per second and a Reynolds number. These are supposed to be roughly of 1.7 times 10 to the 5. Oh, finally, Q is equal to AV. That's gonna give us Q is equal to pi r squared times our new velocity, which is equal to 0.48 feet cubed per second. Very painful process. Um, in the unlikely event where they do ask you this in a exam environment, like a closed book exam environment, they'll probably give you a number that's very close. They might just give you F Hallen already, and just you have to do it maybe once or twice. Um, yeah, again, this is why we have computers, so we don't have to sit here and just do the same thing again and again. So I'll say, just make sure you can do part A. Part B technically is fair game, but it's very labor intensive. Usually, yeah, they would probably you would solve this in Python or MATLAB. Um, so if we compare this, the new flow rate of 0.48 feet cube per second compared to the old one, it actually increased by 20%, which makes sense because we have basically opened the valve completely and we've reduced the filter. Interesting, if you ever go into HVAC, there's a lot of filters in HVAC system. You don't want dust to get into, or you're trying to basically purify the air. You might be tempted to go like, yeah, I'm gonna get the best filter, the finest filter that filters down to like maybe a couple microns. They do use those in like a very specific hospital environment, but you don't want that in majority of residential, even commercial environment. Because when you have a very, very fine filter, the blockage effect, basically the equivalent of K, is very, very high. And then you're gonna have to have a very, very strong pump to blow through it. And a very, very fine filter also needs to be replaced more often. So it's very non-economical. So therefore, quite often they'll settle with something that's like intermediate just to block out some of the bigger debris or dust. But that's technically beyond the scope of this course and the video. If you're interested in HVAC, you can take a MIE 507 by Professor Marianne Touchy. Uh, that wraps up this video on pipe loss.